Welcome to this session, which is on technology. We have representatives of four of the very important, very big manufacturers, and they will give us their insight on technological advantages. And we hope to have some time in the end that I have some questions for them, which I hope they will answer, and perhaps you may have some questions for them as well. So, as not to waste any time, I'll give the floor to Alper Kayan, who is a sales engineer, and he is working for Nordex. So, the floor is yours for your presentation.
Öncelikle hepiniz hoş geldiniz.
First of all, welcome. I would like to thank TWEC for giving me the opportunity to address you. In my presentation, I will speak about some technologies of Nordex. The Nordex blade technology I will be speaking about. I'm Alper Kayhan and have been working at Nordex as a sales engineer for 1.5 years. Let me start with a video about delta turbines. I hope you like it.
Burada türbinin yağı sistemini görebiliyorsunuz.
You can see the yaw system of the turbine and a lateral view of the drivetrain.
Genişletilmiş iç hacim mevcut.
A very large internal capacity. Now we are moving to the hub. You can see the pitch engines here.
Kısaca size
I will shortly speak about the Nordex wind turbine portfolio.
öncelikle
First of all, there are two generations in our portfolio, gamma generation and delta generation. You can see some information about the gamma generation here. N90 2015 means 90 meters blade diameter and 2.5 megawatts of power. N100 2500, 100 meters rotor diameter and 2.5 megawatts of power. For each IEC class, we have a turbine in the gamma generation. Similarly, for delta generation, for every IEC class, we have a turbine N100 3300, N117 3000, N131 3000. The third one has the largest rotor diameter. And as you can see, there's an increase in rotor diameter and power output in delta generation. The these increase the annual production of energy, and there is a difference of around 25 to 30% between the two generations in terms of rotor diameter and power generation. But this is not the only difference between the two generations. There are some other improvements as well. For example, a larger nacelle volume, or active passive cooling system. These are some of the differences, but it doesn't mean delta class is better than the gamma class. These are both type certified turbines in compliance with the IEC standards. Briefly, let me speak about some options. The options for a wind turbine, what do they work for, or what are their functions? They can facilitate grid connection, increase safety, and also increase energy production. Aviation lights. Now I would like to give you information about this. As in every other country, in Turkey, there are some regulations in force that we have to abide by. And in our turbines, 2000 candela lights are used. For day, we use LED lights only, and during the night they are red, and during the day they are in white. These are all LED lights that we use on our turbines. And I would like to emphasize one point. As Nordex, we want these lights to be service friendly, and we want them to be used in the long term. I mean, in the condition monitoring system. So for service operations, it provides important benefits. As you know, inside the nacelle there are some equipments like the generator, the gearbox, and these equipments are periodically monitored. This is compulsory for us. In terms of vibration and acceleration, we are monitoring them. We are using some vibration sensors to this end. Condition monitoring system provides information, periodically reports the condition of these equipment to the service department, and in the event of a problem, the service department can take measures, can take precautions, and this way we can sustain the service in the field. I would also like to speak about the CCV option, the cold climate version option. As you know, when the wind turbines were first established or deployed, they around the Aegean Sea, Izmir, the western provinces were selected. However, now IEC 2A, IEC 3A sites are used, which means the middle of the country, central Anatolia, and towards the north of the country. These are the new locations being used, and in these locations the climate is cooler, colder. Therefore, we wanted to increase the temperature range. For example, in delta turbines, the operation range, the ambient temperature CCV, as you can see, it is for survival -40 to 50, +50, and for nominal power it is -30 to 40. How can we ensure this? We use a thicker nacelle, and inside some of the cabins we place heaters, and in the gearbox also we have some equipment that we are using, and with improvements on the turbine, the operational working range can be improved. CCV light option is for very cold climates. This is an option that we use in cold climates for the gamma turbines. In a standard gamma turbine, the operation range is from is higher, while in this with the CCV light option the range can be from minus 20 to 20. And in the Baltic or Nordic countries, there's another system we are using. We call it the anti-icing system. And this system, as you can guess, is heating the blades and preventing freezing of the blades. This is not currently used in Turkey, this system, but maybe in the future it can be used in Turkey as well. It provides an increase in performance by around 25%, and the turbine operation can continue non-stop 24 hours under icy climate conditions. Rotor blade ice detection system, another system. This system is important for safety and for service. It is very important. The ice accumulating on the rotor blade can be dangerous for the investor. The ice load on the rotor blade can be thrown around the field during the operation of the turbine, and it can be dangerous both for people living in the surrounding area as well as the operator. So we have the rotor blade ice detection system that we recommend for use in risky regions. When there's accumulation of ice on the rotor blade, the turbine stops operating automatically. So also the ice in other components, also the ice on the rotor blades can harm other components of the turbine as well. That is why the ice detection system is very important. I would also like to speak about the CCV anemometer, called climate anemometer. This is an option that investors are asking a lot about. Anemometer is a vital component of a turbine, an important equipment, because based on the data from the anemometer that you maintain the operation, continue the operation in the field. The pitch movement of the turbine is maintained by the information data from the anemometer, and under cold weather conditions we want the anemometer to continue working effectively. We use two anemometric equipments. Ultrasonic anemometer is what we are using. This way we are heating the anemometer and ensuring that it continues working. And now the extended reactive power range. There's a regulation by TWEC, Turkish Electricity Transmission Company, and in this regulation there's a criteria about the reactive power. If it is above 10 megawatts, then we have to abide by this regulation issued by TWEC. How can we achieve this? You can see two graphs on the slide, on the left and on the right. Shown in blue is the figure of Nordex, and TWEC figure is shown in red. TWEC says that in minus 18 degrees the blue line should always be larger than the red line, and the blue line should contain the red line. This way more reactive power is provided. This axis X you can see here shows us the reactive power, and in order to provide more reactive power and in order to comply with the criteria of TWEC, if the capacity is above 10 megawatts, then we use the extended reactive parameter. Customer interface module or CIF module is about the SCALA. there's an NC2 system interface of Nordex, which enables us to display the data online, and the investors with this CIF system can see the operational data, voltage, reactive power, all these data through the CIF module. Fire detection system. It is very important for occupational safety and for the protection of the turbine. Inside the turbine there are very critical components or very critical points from which a fire may erupt. In these points, the possibility of a fire is higher than other points. So we have detectors, and in the event of a problem, these detectors link to the SCADA system and provide information to the turbine monitoring center or to the technicians responsible for maintenance or to the investors. When there's a warning from the system, then both acoustic and visual alarms run off, and this way the risk is communicated to whoever relevant, and then the necessary precautions can be taken. Fire extinguishing system is linked with the fire detection system. In the event of a fire, we pump gas to the dangerous, risky zone, and this way we are preventing a fire before it breaks out. This is a nitrogen-based system. Now I would like to give you some information about the Nordex blade technology and N117 blades. In cooperation with TPI, Nordex started manufacturing N117 turbine blades, and these are the blades for N117 2400 and N117 3000. And are these blades the same for the two different turbines? Of course not. There are certain differences between the two because these two turbines belong to different IAC classes, and the load on the blades are different in these two classes. Therefore, there are minor differences. The blades for N117 are very light. 10,500 kilograms is the weight of a single blade. But there seems to be a problem here, because although the blade of NR50 is smaller, it seems to be heavier. But how could it be possible? We used carbon fiber composite materials so that the blade is more thicker or heavier in one while lighter in the other. So you can see the structural design of this blade. You can see the trailing edge girder, trailing edge shear web, and the carbon fiber composites. And you can see the blade of N100 on the right of the slide. As you can see, we use carbon fiber materials here to make the blade more lighter and more ergonomic. Why is carbon fiber composite material important? It is lighter, 5 times lighter than steel, and more endurable than steel.
Please.
Here you can see the TPI production facility in Turkey. And I would also like to speak about some milestones. In February 2014, the first N117 blade was manufactured in Izmir, and in March 2014, the deliveries across Europe started, and the first blade manufactured in Turkey was used in a project in Finland. Therefore, I should say the blades manufactured in Izmir are used not just in Turkey but in European countries as well. And in mid-2014, erection of the first project in Turkey. I focused on the technicalities, the technical details so far. Now I would like to touch upon some business issues in my presentation. What is the benefit of using a locally manufactured blade for the investors? When you use local blades, then you can have an extra bonus as an investor. This way, you can increase the production, so the sales price of energy is also increasing. In Nordex's current portfolio, you can reach these values shown on the slide. Thank you very much for your attention. If you have any questions, I'm ready to answer them.
Thank you very much. One quick question before we move to the next speaker. You referred to service-friendly when you were talking about the aviation lights. What about the whole wind turbine and its service? How do you have a team of people that service it? Or there are local groups? A quick reply so we can move on.
Okay.
In Turkey, Nordex has this wide web of services, actually wide service web, and there are different types of service opportunities, for example, 5 to 10 year service opportunities or alike, and in any sort of field we can, within the scope of the service agreement, of course, provide our customers with all sorts of precautions and any sort of service operations that they need, which might vary depending on the provisions of the service agreement, of course. Şimdi Sayın Dursun'a dönüyoruz. Siemens Satış Müdürü. 10 dakikanız var. Welcome. Second day, afternoon, right after lunch. Welcome to the session. I will try to make somewhat of a different presentation, starting with the Siemens history. Siemens turbine 33130. And I'll be speaking about reliability in Siemens, and before that I'll be informing you, briefing you about the history or the chronography of wind turbines. Yes, this is the flow chart of my presentation: history and technology, innovation, performance, what's being done, the evolution and the developments in this technology, where it has taken us, and of course then comes the next parameter, performance. And then I will be speaking about the direct drive technology without any gearbox, and I'll be talking about the blade structure and design, finishing up with the tower solutions. Well, let's start with the history. World's first electricity generating wind turbine dates back to maybe 500 BC in the Persian lands, but it was not for electricity generation. The first turbine to generate electrical power was established in 1888 in Scotland. And the technology, of course, was looking onto the windmills, trying to run immense or enormous gearboxes, but the very same year there was the brush windmill. Everybody knows about this one, not the previous one, by the way. Actually, James Blythe was the pioneer, followed by the brush windmill by Mr. Brush, a windmill of 70 meters and 12 kilowatts, entirely made of wings. Then comes another example for us, which is a real example for us all engineers, Lacour, between 1891 and 97 in Denmark. The date is important actually because Lacour has established the formulas, the equations, and established the Denmark wind technology, raising technical staff there, who later in early 1900s have become the pioneers, the avant-gardes of the wind energy movement that he hatched in his mind. Then comes two important other examples, one dating back to 1975, TWEC, 77 actually, TWEC. If you ask who has established the very first windmills, hippies. Surprisingly, hippies, and TWEC is their production, 1.2 megawatts, and there were no areas, no regions that would consume 1.2 megawatts, and they have used some of that energy they generated through the TWEC in heating water, and that water was heated up water was used for heating purposes. And this turbine, TWEC, is still operational, functional. If you have a chance to go there, you will definitely see the elderly couple, 70 years, maybe more, still operating the TWEC. And the first commercial example of wind turbines was erected in 1980 in Denmark, again in its 35th year, and still operational. The previous one was erected by the hippies, as I said, and we are still talking about bringing turbines from 600 megawatts to higher levels. What they have done, TWEC still stands 1.2 megawatts after maybe more than 50 years. So what's the direction of the evolution? Where are its limits? 1997, 1.2 megawatts, the hippies, and we are not so far away, especially in onshore turbines. We are around 3 to 5 megawatts, so we're not so far away. And mostly the turbines are within the 3 megawatt range. 1982, Siemens has acquired the company Bonus. This was the first example of the commercial, and you can see it in the circle with the rotor diameter of 10 meters. That we called the baby Bonus. And the person on the lower right-hand side is the gentleman, is one of the pioneers, Mr. Tisdale, who has set the principles of the three-winged or three-blade turbines and the stone and pitch control, changing power control and ensuring power control by way of revarying blade positions, etc. So he has invented all of those. Today we can reach is up to 154 meters of rotor diameter, generating 6 megawatts of turbine power. That's offshore. We started off with 10 meters of diameter. We have reached 254. There's a standard Airbus comparison, but you can see the little human being, 6-foot person, standing next to the hub. In 1980, that's our 30 kilowatt versus a 3 megawatt nacelle. You can see the nacelle sizes. This is where we're at now. So 10 meters of rotor, 1.3 tons, 30 kilowatts. Where we're at now is 3000 kV, 101 meters, 73 tons. I have chosen the 101 meter rotor diameter because I'll be making a comparison in a moment. Let's scale this. This would be where we would be, well, with the then designs. I mean, if we were to build the turbines with the past technology, it would be 1,320 tons. Where we are at now is 73 tons. So this shows us the technology is advancing, forcing us for higher megawatts, changing everything. And the gearbox, after some point, and I think you are observing this, especially offshore in the open seas, that there is an inclination towards direct drive, because when you are increasing the megawatts, the number of the teeth of the gear have to increase, leading up to higher tonnages. Where we are at in terms of innovation as Siemens. So, where are we? This is our history. The gearbox platform and the direct drive, you can see them on the screen. We are one of the few companies who can work with both. Maybe one of them, the very first, or the only one, I don't know how to put it. We are working with both technologies, and the direct drive technology was developed by Siemens. It was marketed in 2010, but in 2004 we had started the work. We had a couple of prototypes and then commercialized. And then we have changed, right after this, the blade technology. Then we have changed our tower technologies in 2013. Then 2014, Siemens had its own converters. When Siemens acquired the bonus company, we have waited for a very long time to change the equipment inside it. We used it, continued using it, even the equipment that were manufactured by our competitors, because we focused on performance, and we have focused on performance, changing nothing at all, and we had the enough amount of knowledge, number of tests in blade technologies and gearbox technologies, drive technologies, so everything we have changed, overhauled everything. So where we are at now is the 3.3 generation, different rotor blade lengths, etc. What's the difference between? What's so different about direct drive? In the higher classes we provide longer blades. For example, take the example of 330 that we will be talking about here. What have we done so far? Yes, we have marketed this product, started its sales, and we have sold 6 gigawatts so far, and we have a backlog of slightly more than 350 megawatts. That means orders, but just direct drive orders. We have 6 years of experience and 6 gigawatts of sales only for direct drive, the system without the gearbox. 3.3 megawatts, 130, that's the length of the rotor. Not 3, well, S stands for special, by the way. So this is directly class or category 2A, IEC class 2A. How we have achieved this? We have the direct drive technology and the blade technology. We improve their capacity to take on heavier, higher loads at faster speeds. Capacity improvement, and these all take place on the innovation side, on the engineering side. And what matters for investment is one thing only: generation. What do you generate? A single figure, 8.5 meters per second, 16 gigawatt hours, a single turbine. That's the output you can get. You can move between 3 megawatts to 3.3, or 2 megawatts to 3 megawatts to 3.3 megawatts. That's not important, but what matters on the engineering side is the capacity factor. If we're talking about 16 gigawatts, we're talking about some 55% capacity factors. In offshore, this machine can reach up to 55% of capacity. We have the prototype running. Tests far better than we have expected. The pilot series is coming 2016 Q1, and in early 2017 it will be commercially marketed, and the sales have started actually, and most probably in the upcoming months we will be making an announcement of the first sales. Efficiency is the key word, using the least possible space, making the most efficient generation. Why am I saying least of all spaces? Yes, we will have smaller turbines, but we are out of areas, wind farms in high wind areas. So we have to move towards the east, where we have again faster winds. But we have this question which still stands: why do not we use the areas that are already in place in the west more efficiently? The answer is on the screen. This machine with a better performance. Simple. 3.3.130 is an evolution of the DT platform that we had before. Almost everything has been scaled up or down. Nothing has changed. There are improvements, but the mentality has not changed. Siemens has always cherished its integrity for the past 9 years. Everything is either the same or scaled accordingly. And I will not go into the nuts and bolts or the details of this. Let's move on with generation. I have said that this machine is IEC class 2. How about how it can achieve this amount of performance? Well, the power curve of this machine was improvised for class 3. On the engineering side, or from an engineering perspective, I think there are among you who know the best criteria, and the closest we are to that criteria is class 3. So we designed this machine for the best engineering capacity, and that's how we can market it as class 2, but the design is class 3. You can see the increase, 0.2%, but on the right hand side, the annual average wind speed, you can see around 11% or 13%. On the engineering side, what I mean that our focus is on being the most efficient. In Turkey, noise reduction or noise control is not a requirement, but we have still sorted it out. We have a tailor-made, customized for the field, for different speed limits. We have the power curves, and we have, as a company, have the capability to have those power curves to fit for any noise scales. We have also the ice detector system, which provides the turbine controller information about ice buildup on the blades. We have a lighting detection system, which is critical, which is so critical if we're talking about blades, which we will do in a minute. On the service side, detection of lightning is critical. So far, what we can do is to observe it and tell that the lightning took place. And so far, we have used this system to count the number of lightnings, but still we have the capability to ensure best OHS protection. We can count up to 70 lightnings, for example, and still continue the operation without seeing its impact on the turbine. And when we start talking about blades in a moment, I will touch upon this issue. The cooling system is entirely insulated and isolated from the outer environment. Previously we had passive cooling, now we are using active cooling. And in Egypt we have this 2000 megawatt worth sails, as you have heard. Bearings optimized, larger rotors, the bed frame.
Please start wrapping up the presentation, please. Thank you.
Tamam. Hızlı bir şey.
Okay, moving on fast now about the blade technology. You can see it on the screen, the different types of blades which can bear different loads. Our Siemens blades are monoblocks. This is what gives us our upside in lighting, because we don't have different parts in these blades. clearing away the soft spots, so to speak. We have monoblock blades and serviceability. I will just run you through this. We have different options for different scopes, service solutions for different scopes. You can start with 5 years up to 10 years and up to 20 years, 10 years and 15 years in between. So we know our turbine well, and we give you the guarantee of service until the end of the turbine's life cycle. The tower requirement, except for trace in Turkey, we have tip heights that can go above 8,535 meters. Why these numbers? Non-forest areas, and we have a lot of areas where the wind speed does not increase in direct proportion to height. So we are not going up just to be high. We keep it at 85 meters, and if there are no forests, then we just continue with 85-meter towers. So that's all from me. Thank you for listening. Thank you for your attention. Have a nice day.
Thank you, Mr. Erdoğan, for a very interesting presentation. One quick question for you as well. Such a beautiful machine. What about the wind regime, the wind campaign assessment? What do you base your calculations on? You mentioned 8.5 meters. That's an average, but you know very well, better than an average is not enough for siting a wind park. A quick answer, please. Thank you.
Yeah, just a short message from, just short answer to your question. May I have it in Turkish, please?
Please, yes.
Aslında
In fact, in my presentation, I had ideal conditions. Ideal conditions is to ensure Rayleigh distribution and just a normal wind field, 8.5 meters per second average Rayleigh distribution. That's the ideal conditions, IEC conditions, so to speak. So that's what we base our calculations on.
Thank you. So next we'll go to Mr. Yunus, representing Enercon. You have 15 minutes for your presentation, Mr. Isik. 15 minutes.
15 minutes.
Well, I'll be lenient.
Herkese hoş geldiniz. İsmim Yunus Işık.
I'm Yunus Işık. For more than 2 years, I've been working as a sales manager at Enercon, and for 12 years, I've been working in the sector in different firms as a sales manager. I will focus on the current status of technologies and also Enercon and its activities very briefly. The direct drive technology was mentioned in the previous presentation. It is essential for the turbine sector, and since 1992 we have been actively using this technology. This direct drive technology has a certain difference from the previous ones. With electromagnetic infusion, there is the electricity generation here. We use copper wires which surround the internal compartment of the rotor, and this way we generate the electricity, and it is a stable material used, self-induced material used, so you use self-induction. Could we play the video, please? What is direct drive? I would like to show you very briefly in this video. The hub that the blade is turning and the generator are on the same shaft, the axial pin, with the same pace, and this enables less friction, less mechanic problems. This is the direct drive technology. the generation and conversion, electricity generation and electricity conversion are two different stages of electricity generation. In the nacelle part of the turbine, the electricity is generated, and then the components in compliance with the grid receive the electricity, then independent from the grid but in the standards of the grid, you transmit the electricity. So there's a separate conversion system which makes the transmission of electricity. Therefore, stabilization, what enables stabilization in the turbines is the independence of electricity generation and conversion from one another. This way, you can continue to generate sustainable energy as required by the grid without too much fluctuation, and it would be a clean generation that you are making. Available electrical configurations, let me briefly touch upon this. As Mr. Alper also mentioned, there is an FTQ diagram, PQ diagram that the grid requires. At the grid connection point, connection site, your turbine should be able to provide the electricity that complies with the grid requirements. And here, in order to reach the standard of the grid, we provide some optimizations. A larger reactive band, for example, is one of them. And full reactive support in windy weather, STATCOM, is another important configuration. And S2K Q plus option is also important. So we have these different options that we provide as Enercon. Enercon's rotor blades, a bit different from the conventional design. We have a spoiler here which minimizes the air load moving to the blade. This design of Enercon is the one we've been using over the years, for years. This way, the load on the turbine is minimized as much as possible, which prolongs the lifetime of the turbine. And this design also provides another contribution. It enables us to provide you with slimmer designs. This way, you will not have any energy loss. With this design, for example, the turbine, there's an energy efficiency increase of around 10 to 12% depending on the type of turbine you are using. And the new rotor blade design, the blade tips have been optimized. The blade tip is similar to that of a Boeing aircraft. And this way, with this optimization, there is lower noise emission and the power output is higher. This is only available at Enercon. In Class 1 sites or fields or Class 2 fields with 8.5 or higher, we provide storm control. In stormy air or stormy wind, as you know, when the turbines reach a certain level of storm, level of wind, they automatically close down in order to protect the components of the turbine. With Enercon storm control, the turbines do not switch off at the typical cut-out wind speeds, and they continuously adapt their power output. I would also like to speak about the different turbines. We have sub 1 megawatt, 2 to 3000 megawatt, and higher than 4 megawatt turbines. So we have a new series of 4 megawatt turbines. We have introduced this new series. From mid 2017, these will be in use actively. A prototype is deployed in Germany nowadays, and it will be marketed in Turkey from mid 2017. The rotor diameters are growing, increasing continuously, but of course a time will come when we will no longer be able to make them larger, so we have to protect the rotors, the blade very well. At first, on paper, you may provide a very high power output, but you should make the feasibility studies in a very detailed manner. You need to consider 2 or 3 decades from the current time. That is how you should make your design. EP4 for megawatt platform takes this into consideration. Now let's see the video.
Temel dizaynında yaklaşık %10'a varan eski tasarımlara göre bir beton azaltması gerçekleştirdik bu üründe. Daha optimum, daha ergonomik güç modüllerinin yerleşimi söz konusuydu. Burada gördüğünüz bir beton kule, özellikle 85 metre ve üstünde hibrit diye tabir ettiğimiz hem betonun hem çeliğin olduğu, karışımı olduğu kule tiplerini kullanıyoruz. Uzun yıllardan beridir de Türkiye pazarında da olmak üzere aktif bir şekilde kullandığımız bir kule tipi. Bu gördüğünüz rotor kısmı üzerine sarılan pole shoes dediğimiz kutuplar. Jeneratörü 2 parçalı ürettik. Bu da yenidir. Neden böyle? Çünkü bu bahsettiğimiz türbin bir 126 metrelik bir kanal, 127 metrelik.
This is new because this turbine will carry a blade of more than 100 meters. So only the blade of the turbine is not enough. We should also increase the length, the size of other components as well, because only increasing the size of the blade would not be sufficient. You need to develop other solutions to fit the larger blade size as well. In the smallest turbine, we have a spoiler. It is standard for all turbines, the spoiler. The trailing edge serrations, as you can see on this slide, it is to minimize noise. It is on the blade and minimizes noise. And also you can see on the video how heating of the blade is performed. EP4 means Enercon Platform 4, and this is a class 2, will be marketed as class 2. 135 and 45 meters will be the 2 different types, and I should tell you that there will be further new classes in the future. EP4 series, as you know, ISE standards certify turbines for 20 years generally, but EP4 has a certification of 30 years. This is the first of its kind in the market. So our investors are long-term investors. Therefore, in their feasibility studies, I think they will take this specific feature into account. I mentioned optimizations were made. What has been done as optimization? This turbine should be stable. Less components means less problems for us. But this is not enough, of course. The production, the manufacturing of the turbine is, yes, it is very important, but also what is equally important is to adjust the turbine to different weather conditions, very different geographical locations. I mentioned the blade, there's lighting, detection, protection system. I mentioned it is optimized and it is slimmer. Also, the energy output is not sacrificed for making the blades slimmer. I should especially say this. From aerodynamic perspective, E126 and E126 EP4 are compared on this graph, especially in terms of energy output and in terms of the design. There are very important optimizations. And I mentioned the trailing edge serrations. There is a significant noise reduction in E126 EP4, and this is standard for turbines with more than 2.5 megawatts of capacity. And the nacelle, the structural concept I would like to mention, the materials, the quality of the materials is very important because it would also make the turbine of a higher quality. If your material technology is good, then your turbine will be good and its lifetime will be very long. And it will endure different conditions better and it will require less maintenance. Therefore, cast technology should be very developed. Cast technology is very important for us. I mentioned the generator, that there are two separate components of the generator, and you can see how it looks logistically. And I mentioned the tower and foundation of the turbines. As you know, earthquake is an important risk in Turkey, especially in those places where wind turbines are deployed. Therefore, earthquake resistance is very important in Turkey. And for years, we have been working on this, and we are very experienced in this respect. So we are providing the same quality with less concrete and different materials. I mentioned direct drive, so I will skip this part. And the options I mentioned to you in my presentation, what do these options provide you? Frequency control and also fault ride-through. In terms of short-term faults, for example, the grid control may say 1.5 seconds, but for 5 seconds, you can see there's no problem at the turbine, and it also prolongs the lifetime of the turbine. This is important. Inertia emulation, it is also important. And now very briefly, what does Enercon do around the world? The installed capacity of around 39 gigawatts, like it equals to the size of 10 football fields, and it has production facilities worldwide, also including Turkey. And apart from some specific materials, almost all materials are manufactured in Enercon's own facilities, own factories. In Turkey, in Istanbul, Izmir and Ankara, we have 3 offices.
Please start wrapping up the presentation.
2 slaydım kaldı. In Turkey, as I mentioned previously, there we have local incentive, feed-in tariff. We have a rotor blade production facility in Turkey, in which we have been manufacturing blades actively since 2002. And about the tower, concrete and steel towers are produced. So we have a hybrid production. The concrete tower is manufactured up to 135 meters in our own facilities. Thank you very much for your attention.
Thank you, Mr. A quick question for you too. I was lucky to visit the Enercon facility in Germany and went up the 7.6 megawatt wind turbine. So
7.5.
when is the 10 megawatt or even higher coming up? A quick answer on this one. Is it on the cards?
Actually, there will be we are producing, all turbines are producing the energy from kinetic, and there will be mechanical stress if you go to big turbines.
There are already 210 megawatt. You know them, the Sea Titan and the Sea Weather.
But we are working only on onshore.
Okay.
So therefore we don't see that it's a requirement that it will be reaching 10 megawatts. But we don't know. Future will show us.
Okay.
So we will see.
Thank you.
Yeah.
And now, last but not least, Mr. Nis Turesey, representing Sevion, and he is the head of the department. You have 15 minutes as well.
Distinguished colleagues from the sector, dear participants, welcome to our Congress, first of all. And I have this little video clip providing you with brief information about the company, and then I'll be moving on with informing you about our portfolios.
Sunumu açabilirsek teşekkür.
If I can have the presentation on the screen, yeah. You have seen the video. We are active and we're well known in offshore technologies based in Hamburg, Germany, composed of an amalgamation of many other companies. Repower then changed our name to Senvion in 2011, around 2011 and 2014, and we are actively present in the sector. In 2001, when the companies merged, Approximately 132 megawatt was the capacity, total capacity of all the companies with 142 employees. Looking at 2014-2015 now, we have reached a staff of 3,731 people with almost 3 gigawatts of generation capacity. The successes of our company are abundant, actually. About 332 megawatts offshore project we have undersigned in the time between. In Canada, we have also entered an agreement for another 150 megawatts, 172 megawatts in Portugal in 5 wind farms. Those are some of the projects. Then we have offshore products, 6.2 megawatts, 126 turbines, 18 prototypes have been set up, and we have been acquired by a $25 billion fund by US, which has accelerated our investments, and we are so keen on entering and setting up ourselves in the Turkish market, and that's the focus of our work in Turkey. I'll be informing you about our products in a bit more detail, but you can see 3.4 M140 and 6.2 M126 turbines, and we believe there is enough room in the market for these products. Let's take a look at our technologies, how the turbines have developed. We have started off with the MD generation or series MD products, lower than almost 1 megawatt, and we have stepped into 2 megawatt turbines. We have marketed those products, started working on offshore as well. We were speaking about 3 megawatts in onshores, and we have introduced in the market the first 5 megawatt offshore product, and we exceeded that towards 6 megawatts in the offshore, making ourselves the leader. Then, apart from 2 megawatt platforms, we have 3.4 megawatt generation, or the product GAM. I will give you the details later. For class 1 fields, we have 3.1 and 114. For class 2, 3.2, 122, that's the rotor. We have developed for class 3 as well. So we have all these models. And let's take a look at how the turbines have developed. Let's touch quickly upon the offshore. We started with 5 megawatt or 5M series, and in the market it resounded actually, because it was a leap from 3 to 5 megawatts. The entire turbine structure changed. Then we have moved on with vertex generators with some touches or trimming the blades, and we have increased in our 6XM series the product lifetime up to 25 years. So as I said, we started off with the MD series, lower than 1 megawatts. Moving on with MM, we have moved into 2 megawatt class. We have changed the blades, the design, and we have modified some issues. There we got the MM series, and we had almost 4,000 MM turbines sold worldwide. Then on this platform we have developed, on top of this platform we have developed 3XM, 3.XM platforms with a blade length of more than 100 meters. We're talking about the 3 megawatt class still. And finally, the latest developed product is the next electrical system, as we call it, with the full converter system, which is more grid compliant, with more updated versions of products reaching up to 25-year lifetimes. So we have started marketing these products very recently. And the MM series, you can see the 2 megawatt class, MM82, MM92, and MM100 are the 3 products under the MM series. MM82 is for class 1 For strong wind situations, MM92 is again between class 1 and 2, and MM100 is right sitting in class 3. You can use in class 3 areas, IEC class 3. Let's take a look at 3XM series. We have plus 1, plus 2, plus 3 models. We have worked on the platform. Of course, the product or model development is based on platforms. MO1 104 is being established in Izmir. Successful in class 3. So we're looking for the best of performance. And these products especially are so efficient, so effective in class 2. M114 has started off 3.5114 actually, then we started using the FG model, voltage generator actually, increasing efficiency. And then comes again the final product in class 3, 3.0 M122 with a maximum efficiency at low wind sites. I will give you another video, show you another video at the conclusion of this presentation. You will see the lengths of blades for areas, of course, to make best of the areas with lesser winds. That leads us to increase the diameters of the blades. And 6XM series, mostly offshore wind farm products and for deep waters, of course. But in the upcoming 5 years, I believe there will be enormous developments in this area as well. 6.2 M126, we have two lengths of rotors, 126 and 152 meter models. Here's a question that we often get. Can we use these onshore, these turbines onshore? Yes, you can use them in areas close to shore because these are offshore turbines, and the reason we are not using them onshore relates to logistics actually, transportation. It's not so easy taking these turbines, which are heavy structures. We're talking about some 152 meters of blades, well, and almost 6 tons of generators, so it's not easy to transport them. Let's swiftly take a quick look at these models. MM82 sweep area, 5,281 square meters. Hub heights, 59, 69, and 80 meters. And logistically speaking, this is below 70 tons, maximum logistical weight. And the sound power level, which we don't talk much about in Turkey these days, but I think in the future we will be. So the sound power level, we have to observe certain legislation or provisions in terms of reduction of noise generated. So 104 decibels is the generated noise. MM92 area of sweep, 6,720 square meters, 64 meters, 69, 80, and 100 meters. These are the hub heights, and the noise, again, 103.2 decibels. Here's an 103.8 decibel product, MM100, 7,854 square meters of sweeping area, and hub heights optional between 75, 80, and 100 meters. And the noise level, as I said, 103.8 decibels. 3XM, you can see 4M products, 104, 114, 3.2114, 3.01, 22. These are the versions. And we have different models on the right hand side. You can see on the top the next electrical system variations, and these products offer you a rotor diameter of 104 meters, almost 8.5 thousand square meters of sweeping area, hub heights, and less than 60 tons. These turbines, the heaviest one is less than 60 tons. How about 114? We have a swept area of 10,000 meters, 200 7 square meters. Hub heights 93, 119, 143 meters of hub heights. And 3.2 is no different than the previous one, still 10,207 square meter of sweeping area. Hub heights, you can see 93, 123, 143 meters and less than 60 tons. 3.0 M model for low wind areas, or for areas where wind is not strong. Class 3 areas will be taking the lead in Turkey in the upcoming term. So this is the model for those areas with a sweeping area of 11.6 thousand square meters. Hub heights, you can see, varies between 89 to 139 meters. Well, why 89 meters? Depending on site conditions. If there are no obstacles on the field, you can have these options: 89, 119, 139 meters of hub heights and 104 decibels of noise. 3.2 M 122, we have the electrical substructure, which is quite different. We have 11,690 square meters of sweeping area, different hub heights. Actually, we are working on these still, but you can vary hub heights between 89 to 139 meters, 106 decibels of sound power level. Then I will be sharing with you the video of this one. We have launched this product. This is the newest product, actually, with a rotor diameter of 140 meters on the market, with a sweeping area of 15,394 square meters. We have different hub heights. You can see the variations, and different variations will be marketed as well. Electrical system is more grid compliant, as I told you before, and the noise level, again, 104 decibels. Quite reasonable. And if we can watch the video, that would be my final words.
Aslında bunu değil, öbür videoyu istiyordum.
I was expecting the other video, actually.
%122 ile kıyasladığımız zaman %20'lik bir artıştan bahsediyoruz.
We're talking about some 20% increase comparing this one to the previous platform. This is based on TWEC platform. We have installed capacity of 600 megawatts, turbine based, presently. As I said, it's the next electrical system, more grid compliant, as I said. You can see the blades, the rearrangements in the blades. A 68-meter blade, it is. (104 decibel noise emission). 25-year operating life, which is critical for investors and also in their feasibility studies. Capex wise, of course, if you're bidding for tenders. This one, 140 meters of blades. You have to have a feasibility study for this. You cannot fit this turbine into each and every field in Turkey, and you cannot say that, but there are low wind areas and areas where transportation would be easy. So this is fit for those areas, and I think we'll be moving on to the questions and answers. And if you have any questions addressing me, I'll be most happy to respond to those questions.
Thank you very much. A quick question, just to be fair to you as well. Are there any plans for offshore in Turkey?
Yes, I mean actually, but of course the important thing, maybe it's much better if I answer in Turkish also.
Please do, yeah.
Well, offshore-wise, yeah, it's a market with a great potential in Turkey, and the seas should be shallow actually. There are some basics, and there should be some developments regarding the foundations for the turbines, but in the 5 years to come, there will be technical developments, design-wise other developments will come, and that market will flourish in Turkey as well. Teşekkür.
A big discussion, and we will have to do that one day as well. Okay, we have a few minutes. Are there any questions from the audience? Somebody? If not, okay, the gentleman there. Wait, get your microphone.
Okay, I'm going to ask in Turkish.
I come from METI, Wind Energy Center. I would like to ask this to Enarco. You are using the blades. You have shared them with us. Could you... We have seen the tip blades in your products, and we don't see that in other products. What is the reason for that? Well, the tip blades and that development of the tip of the blades has a reason. As I have said in my presentation, we want to end up with slimmer structures, blade structures, reminiscent of the airplane wings. And then we focused on the turbulence and turbines. When you do microsighting, you talk about some 5-7 rotor diameters. When you're locating the turbines on the field, you have to position them apart from one another. So the ones in the back, the turbines in the back, might be impacted by the turbulence of the one standing before it, and this creates some aerodynamic concerns, not only at the tip of the blades, but also at the egg shape, at the body of the turbine. Hence, the egg-shaped turbines, to prevent or minimize the wake effect of turbines standing in the front on turbines standing in the back. That's our R&D focus. That's how we developed it actually. We have optimized the wings, reducing the turbulence, and as I said in my presentation, enabling much more effective sweep area use.
Any other question from the audience? Because I have one I want to... Oh, the gentleman there. Lives in Turkish. I'm the only one who doesn't know Turkish.
My name is Batuhan. I would like to address Mahir Bey, the gearbox. And you said you're not using gearboxes, and do you think other companies would move in the same direction as you? And you said it's more efficient and effective, but you didn't dwell on this issue, go into the details. Well, Yunus and I, thank you for the question, by the way. We are working on two different technologies, gearbox technologies, direct drive technologies without the gearbox. And I said we have both, I said. Because in 80s, since 1980s, we have been producing gearbox machines, reliable machines, durable machines, and we are claiming since that we are the most reliable company in this regard. And why we have moved towards the gearbox, the system without the gearbox, or the direct drive technology, actually Yunus Bey touched upon the issue regarding our differences our drive mechanisms, we use a permanent magnet system which is lighter and that's more efficient for offshore areas where you won't have logistics or transportation problems, challenges. And as Yunus Bey said, the mechanical train, the rotary train, the amount of rotary train or the moving parts had to be reduced, hence the direct drive technology. What we had in mind was the tonnage. We had 3 megawatts with the same weight, 73 tons, and we have taken most of the mechanisms out. The rotary equipment, rotary parts, we have reduced it, and still we could have the same efficiency. And engineering, speaking from an engineering perspective, the lesser the amount of mechanical parts, moving parts that you will have more serviceability. So the future lies in direct drive. That's what we think.
I think we're running a bit late, but I have one question that I will not leave without setting. So it will be quick, and I hope you give me a quick answer as well. In this past day, or even the day before, there is a lot of discussion about Turkey becoming a hub, a regional hub. There are countries to the south and east of Turkey which have huge potential and no development at all. So really it's a huge ground to enter and play. On the other hand, there is also discussion about creating, constructing, designing a Turkish wind turbine. Those two tying together, if you wish. People have done it, the Chinese have done it, and of course they're using their turbines only in China because they're not certified anywhere else. We've done it in Greece as well. There is a wind turbine, Greek design, 400 kilowatt, standing in a park working. No other turbines were constructed because we didn't have the development. You are both Turks, therefore you want your country to perform well and prosper. On the other hand, you represent companies who may suffer if a Turkish wind turbine is produced. In 1 minute, your idea about this discussion, what do you have to offer to that discussion?
Okay. Again.
Well, my general director being among the audience, welcome. And it's going to be fun for me to respond to this question about settling down in the Turkish market. Well, it's one thing. It is important. It has to happen. And the sector is waiting for this to happen, actually, because we're talking about a 1 gigawatt sector. And more than discussing these issues, we should take for concrete steps, and that we do as the company. And we might create our own components. We might set up the sector and the components ourselves. Well, if you confide in your own technology, there's nothing for you to be scared of when you see any components, opponents, whatever, competitors. But in the name of developing the sector further in Turkey, we are ready and willing to take further steps. Thank you. Enercon in Turkey is one of the leading companies in Turkey. Again, I would like to emphasize this once again, and it is a well-known fact by the shareholders in the sector. Since 1998, we are actively running turbines in Turkey, using operating turbines, and in Turkey we have about slightly more than 1,000 megawatts of installed capacity in Turkey. This means that we have more than 700 turbines. So we have made, yes, certain investments for the towers, for the blades. And on the other side, we have the policies, and we cannot see clearly the direction in which they are moving. Of course, we always share our opinion, our views, recommendations, you name it, with the authorities. And the clearer the picture, the further steps the manufacturers will be taking. It's a great market, enormous market, some 40,000 watts. And as Enercon, we are ready to play our part, make sacrifices sometimes. If that's needed, we are employing, by the way, more than 700 people in Turkey. And when we are ready and taking these steps, we are looking forward to having the incentives, the support, the backing behind us, and those steps we will be taking in unison, in harmony with respected parties, of course, and we need a clear picture ahead of us. That will be my comment as Enercon. Now Siemens. Becoming local or native. We are in this market. We are here for the last 160 years, and the same thing goes for other 170 countries. We have more than 3,000 people working in Turkey, 3,000 employees, and we have 3,000 employees. Do you consider such a company a national company, domestic company? Yes, of course we are local. And about localization in turbine technologies, yes, we are doing our best. And once the conditions are in place, we are running our communications. Our communication lines are live, and we know the developments, and we will do our best to the top of our capacities about localization. Local turbines, domestic turbines, if we want to do it. So I'm taking my Siemens hat off. Then we have this question to answer. While manufacturing the national turbine, and we are financing this, are we going to be able to compete with other companies? If that's a yes, the answer to this question, then our national turbine will start rolling. So there has to be a financial solution to this, that the domestic or the national turbine requires finances for being able to survive. I don't think differently. Nordex in Turkey, since 2009, 1 gigawatts of power is in the horizon. And in the future, depending on what the legislations would bring, we will sit around and talk about it and see altogether what happens then. So I agree totally with my friends.
Just said in the end that being your neighbor, and I watch your progress, and I admire your progress, and I'm happy for your progress. My friend Mustafa keeps me informed. I can see there are problems, but you see them and you worry them and you want to solve them. Believe me, for me as an outsider, I think everything is going really well. Your development is very good. Keep it up. Solve the problems. Make it better. You are in a winning streak, and don't lose the sight of that. Please join me in thanking those four gentlemen for their fine presentations, and goodbye.
Değerli misafirler, Yenilenebilir Enerji Genel Müdürümüz Sayın Münif Karakılıç da
Mr. Münif Karakılıç, the General Director of Renewable Energy, Münif Bey would like to give you your certificates with your applause, please.